Sponsored by Razer and NVIDIA. This is a high-powered rocket with a control system embedded into the aft fins. The rocket will fly at speeds up to Mach 3, and it has a blunt-nose copper tip so that we can cook a piece of meat using the aerothermal heating that happens at that speed. Whether it's the Christmas tree rocket, the hot glue rocket, or now this, I love a high-effort post. The control tabs are made of anodized aluminum and they're driven by MKS 6160 high-torque servos. These slim servos are embedded inside the fin, which is made of solid carbon fiber. The pockets are then potted in epoxy to smooth out the outer mold line, and then the fins are attached and filleted to the body tube. The fins were cut out using the Carbide 3D Shapeoko router, but before we get into more details, this video is the beginning of No Effort November, a month during which I put no effort into making videos. I got this idea from Technology Connections, one of my favorite channels, and I think it's a great reminder that you can put whatever you want on this platform. And what I want to put on this platform is a long technical deep dive into how I made this rocket airframe. So let's start at the beginning. Before cutting the fins out in carbon fiber, I started with wood, specifically birch because it's so cheap. The carbon fiber that the fins will eventually be made of is very expensive for reasons we'll cover later, and birch provides a great way to test out my tool paths. The path uses 2D adaptive clearing for the servo pockets and shallow contour passes for everything else. On the first test cut, I included the leading edge chamfer on one side, but this presents a problem. How do we get the chamfer on the other side of the fin? My initial plan was to mill all 4 fins at once, flip the entire stock material upside down, re-index it, and then mill the other side. But then my buddy Winston Moy had a better idea. I cut out the fin using the same strategies as before, but left off the leading edge chamfer. On the other side of the machine, I set up a fence and indexed the fin against it using a piece of stock material as a spacer. This should let us get consistent x-axis placement, which is important to determining where the leading edge chamfer is. Then I ran a parallel tool path to create that chamfer and flipped the fin to do the other side using the same path. This creates a consistent chamfer across any fin that we align to this fence. With the tool paths complete, you'd think it'd be time to make the fins, but it's not. It's time to test the servos. The servos I'm using here are MKS 6160s. For the amount of torque they put out, these things are relatively slim, and they're designed this way to fit inside the wing of a UAV, which we're kind of doing. Like, in a sense, a rocket is a UAV, and in a sense, a fin is a wing. The servos claim they can do 18.6 kilograms/centimeters of torque, which is a ridiculous measurement for torque, but let's just roll with it. 18.6 is an impressive claim. The distance between the center spline and the actuation point is about 9 millimeters. And mounting this servo in a vise with a crane scale and some ratchet straps, I set about to find out if that was true. I would like to learn 2 things. 1, what is the maximum torque of the servo? And 2, when we exceed that max torque, what happens? Is this test a little overkill? No. Usually I'd say yes, but absolutely not. We're putting 40 pounds of rocket propellant into this thing. It is an enormous vehicle. It is fully guiding itself. It needs to be fully in control, and we're trying to prove out tech for the space shot. I need to be doing this at the level of risk tolerance that I'm going to be using for an 8-inch rocket. For what it's worth, a 4-inch rocket will kill me just as good as an 8-inch. I mean, you can get killed by an Estes-like park flyer, but the secret goal of the meat rocket is to show that I'm ready to build something much larger. So let's test this thing. With the initial testing, I held the servo down at its center point and started ratcheting down the ratchet strap. I was able to get some pretty incredible values for this. The units on the crane scale are in newtons, and it got to the point where the force started unwinding the steel cable attached to the servo. With this style of testing, I found the maximum resistance to be somewhere around 650 newtons. So it will really hold that position for a long time. And if I let it go, it does seem to lose a little position. Like, that is not the center I was looking for. This is almost 60 kilogram/centimeters, which way outperforms the spec. But the servo clearly slips during this process, and it seems like what I'm actually doing here is just bending the metal of the gear train itself. Eventually, when I tried pulling again, I did strip the gear train entirely. Oh, that broke something. Yeah, there we go. I then ran testing where I attempted to move the servo under load. This yielded some less encouraging results. The servo can withstand enormous static load, far beyond the spec, but I did notice that when trying to move the servo under load, I was getting below the spec. The numbers I was getting were somewhere closer to 11 kilograms/centimeters instead of 18.6, which is a stark difference. All right, gang, new idea just dropped. This is like a shaker. Sometimes we desire more performance out of our devices than they are willing to give us, and they need a little convincing. Sometimes that convincing comes in the form of more volts. The servo I am using is rated to 8.4 volts. That's a 2-cell LiPo. This is a 3-cell LiPo, which brings us up to 11.1. That's higher than the servo wants to be at. And yes, I hear you asking, Joe, do you really think it's a good idea to overvolt your servos in such a high-stakes environment? To which I would say, shut up. Let me make this mistake. I know it's not a great idea, but consider the following. I really want to do it. All right, let's feed this 11 volts and see what happens. 231, 211, 200. Servo's a little hot. Wow, dude, the overvolting is great. This is excellent. What could possibly go wrong? The servo didn't die using 3 cells, so naturally, because we're testing to failure here, I went up to 4 cells. 217. Oh, that's it. There's the smoke. The servo did not like 4 cells, which makes sense given that's double the rated voltage. The next test I ran was a runtime test. Using a program on an old Signal computer, I drove the servo back and forth under a little bit of load from a rubber band for as long as it would go for. Using the overvolted 3-cell method, I was only able to get about 4 minutes of life out of the servo before it started slipping and dying, and when I ran the servo at the proper voltage, I was able to get about 17 or 18 minutes before the servo died. This prompted me to do one of my favorite things, which is cold call the company I'm interested in. I found a customer support number for MKS servos and spent a little while on the phone with them. When I asked them why their servos weren't delivering the stated torque on the packaging, they said something to the effect of, "What are you gonna do? We gotta sell servos." And it's like, what are you gonna do? Don't lie about the torque. For what it's worth, they were really nice on the phone, and the call yielded a much more detailed spec sheet that gave me an idea of where and how I can expect the servos to fail over time. With a coreless servo like this, heat is going to be the thing that kills it, specifically heat within the motor. So constantly cycling it back and forth has a pretty high chance of burning it out, but intermittent movement or movement over the course of a flight profile like I'm going to do shouldn't be a problem. All that information is good enough for me to move forward here. In flight, we're going to operate with 2 cells like the servo wants, and we'll design the control system such that it doesn't demand more torque than the servo can actually do, not what it states on the package. I want to press pause here and back up a little bit. I haven't talked much about the fin tab sizing, the nose cone shape, any of the GNC analysis, and all of that is really heavy simulation work, specifically stuff with CFD, or fluid dynamic simulation. Up until now, I've been doing that simulation on an old laptop from 2020, and this approach works great if you don't have deadlines and don't care that it takes multiple hours to run a single sim. Thankfully, this video is sponsored by Razer and NVIDIA. I've been using the Razer Blade 16 with the NVIDIA GeForce RTX 4090 for a few weeks now, and this thing is a beast. I've also been switching to a more powerful CFD software, but that's a harder comparison to draw, so let me give you a different one. I edit most of my videos using Adobe Premiere, and with the computer that I was using, it would take somewhere between 1 to 2 hours to render out a full edit. What you're seeing is me rendering out the cross-section video that I published in September, which takes a long time. Perhaps this is obvious, but I make a bunch of videos, so that time adds up. Rendering out the same exact project with the same settings on this machine yields a less than 10-minute render time. That's like unthinkable for me, given my current setup. The GeForce RTX graphics provide accelerated rendering for all sorts of applications, not just video editing. And this is super nerdy, but the DCI P3 color space and the 240Hz refresh rate are also like big winners for video editing. All of this is powered by the NVIDIA Studio drivers. The GPU accelerated encode speeds up exporting of videos, and the GPU accelerated decode enables smooth playback and scrubbing of high resolution and multi-stream videos. With a bunch of upgradable RAM and storage, best-in-class build quality, and a bunch of cool skins like this one available, this computer is a huge upgrade for editing and simulation for me, and it can be for you too. You can do that by visiting the link on screen or in the description below. Thank you so much to Razer and NVIDIA for sponsoring this video, and now let's get back to it. With the servos done, it's time to cut out these fins. I secured the stock material to the table using X-Fasten double-sided woodworking tape. I used a birch wasteboard under the carbon fiber and smoothed it out using this comically large 8-inch piece of stock material, and the carbon fiber goes on top using the same double-sided tape method. This stuff is half-inch thick, quasi-isotropic dragon plate. Dragon plate is expensive, but it is really good. I could have laid up my own carbon fiber sheets for this, but I opted not to because I want the absolute best of the best chance that these fins don't flutter themselves to pieces at Mach 3. There's a lot of unsupported area near the servo, and unfortunately, an $800 sheet of carbon fiber is kind of a drop in the bucket for a project like this. The sheet is also quasi-isotropic, which means they put the layers down in alternating directions, and that helps with strength overall. Carbon fiber is like worse for you than asbestos. It's so bad. So I'm using a HEPA filter bag in the shop vac, and the CNC machine has a dust boot on it to make sure that it sucks up as much as possible. But in addition, I'm also wearing a respirator and eye protection and usually some form of gloves as well. The dust here is so bad for you that some people cut carbon fiber underwater. I'm not going that far. The dust boot and a HEPA filter and a respirator and eye protection is probably enough, but you don't want to breathe it in. I'm cutting this using a flat carbide 1/4-inch end mill. With carbon fiber, you should really be using diamond tip stuff, something that will maintain its sharpness because carbon fiber wears it down quite good. And I did buy the right cutter for this, but it did not show up in time and I was getting impatient, so I cut the fins this way. The wear on the tool over time becomes clear. The first fin cuts out all right with a little bit of fraying. The second fin gets much more fraying on the contouring pass. And by the third and fourth fin, the tool is doing a lot more ripping and a lot less cutting. The final shape comes out just fine, and a lot of the frayed area can be fixed with a little bit of sandpaper. But if you're wondering why this looks disgusting, that's why. Exactly like the birch version, these fins were indexed against the fence using a piece of stock material, and then a parallel toolpath was used to create the chamfer. In hindsight, it might have been better to start the toolpath on the edge of the fin rather than from the side. Any good machinist knows that cutting with the side of the tool is always better than cutting with the bottom, and with each pass I was essentially plunging it down into the stock material. This resulted in a kind of horrifying and comedic fraying that happened. Just as with the birch, the fins came out fine, but they needed a little bit of sanding to look good at the end. The fins are not identical, by the way. They're made in pairs. In theory, the servos create a little bit of asymmetry, even when potted in epoxy, on the final surface. By making these fins in opposing pairs, any asymmetries we create with the cutouts should be cancelled out by the opposite pair of fins. In practice, I'm not sure this matters that much. There are asymmetries all over the vehicle that are probably more significant than the fins, but I have the option to make them this way, so why not try to minimize that where we can? In my concern about the stiffness that's lost in the fin by the servos, I took an interesting little detour. I took apart one of the dead servos and tried to etch the aluminum surface that wasn't seemingly anodized. In hindsight, I think all of the surfaces are anodized on this servo, it's just that this one section has red coloring. My goal here was to create a better surface for the epoxy to bond to. Anyone working with aluminum should know that the oxidation layer on the surface of the aluminum can make it really bad to bond with. So after chemically etching the surface, I put it in an allodyne solution for a little while. This turns the parts a beautiful gold color, and it probably did increase the ability to bond epoxy to the surface of the servo, but if they're already anodized, which it seemed like it was from the etching behavior, and for the amount of complexity and headache that it was to actually get this right and try to reassemble the servo, it did not seem worth doing. The servo gets embedded into the fin using epoxy. There's no hope for serviceability here. If the servo dies, it dies and the whole fin dies, and if it's attached to the vehicle, the whole vehicle dies. At a larger scale, it'd be nice to prioritize serviceability, but serviceability at this scale comes at the cost of stiffness in the fin. I want epoxy or some type of structural material in every part of this fin that I can get it. We must remember, as we do this project, Mach 3 got hands. There's also something to be said for the complexity involved in trying to machine access hatches for every part of this fin. At some point, you just test the servos as good as you can, and you send it. To make sure I had this process down, I attached a dead servo to a 3D printed control tab and put it in the birch fin. I'm really glad I did this. This is an extremely nerve-wracking process because if you get it wrong, you ruin the whole fin. So having a practice run was a good idea. For the flight servos, I bought 6 total and selected the 4 best ones as far as I could tell. I tested each servo thoroughly and picked the ones that seemed to have the fastest or most consistent response. I chopped off the mounting points too. We don't need these here since we're using all this epoxy. The servos themselves can't support all the aerodynamic forces involved, so the tabs are also pinned on the other side with an 1/8-inch stainless steel dowel. I drilled the hole in the base fins using a 3D printed guide that I designed. This worked okay. It wasn't great. The drill bit can travel and weave a little bit inside the carbon fiber, so I'll have to come up with something better in the future. Glad I tested it though. The servos are first attached using Loctite 9340 high sol. This is a relatively thick structural adhesive, and I added some thermocells into the mix to thicken it further. I began by coating each surface early on to let the epoxy sort of soak into the material, and then waited a little while until the epoxy became a bit thicker, at which point I pinned in the servo and control tab. This is a kind of under-constrained problem. You're epoxying the servo to the control tab at the same time you're epoxying the control tab and the servo to the fin. It just means the whole process is kind of stressful. There's a lot of things that can go wrong, and I think some 3D printed jigs and a little prevention for the epoxy getting everywhere could fix this in the future. Traditional razor blades ended up being pretty good spacers to keep the control tab from bumping against either side of the carbon fiber. Once everything had cured here, it's time to run some extension cables. The PWM extension needs to run all the way up the vehicle, but we'll start with just one length of it. Here's a little bit of foreshadowing. At every step of the way, I'm plugging in the servo to make sure things still work. At any point, if things stop working, we're totally hosed. It's Jover. These servos are epoxied in, which means they stay in there forever. I'm soldering the extension directly to the servo cable. There's no need for a connector here, and the connector just wastes valuable space. Much like I did during the roll control testing this spring, I'm staggering the connections for each wire in the cable so we don't need to insulate them. It's a little finicky to get all three joints to line up this way. Sometimes there's a little slop in there, but for the size of the raceway they have to run through, it's totally fine. Before potting all this in epoxy, I CA'd the servo cables in place. This ensures they stay below the outer mold line of the fin, and that they don't try to pop up during the epoxying process. I also tossed small pieces of aluminum tape across the exposed motor section. The very aft of the motor has a little bit of a hole in it, and I was worried that epoxy might be able to seep into the motor itself. As before, with the servo leads connected and CA'd in, I tested each fin.
That's fine. And that's not. Is this dead? What's happening? Do you think it's the tape?
Initially, I thought it was the aluminum tape doing something weird between the grounding of the motor and the aluminum frame of the servo, but that doesn't really pass a smell test since they should all be grounded the same.
Oh, this is so bad. What's happening? Oh! Oh my god! Dude, I think I might actually be stupid. Carbon fiber is conductive. I'm actually stupid. Wow. Okay.
The connection between the servo cable and the extension cable is unshielded. This was fine in the roll control testing that I was doing earlier this year, but it's not fine here. The earlier test flights, the fins were PLA, so they're non-conductive, and so long as you staggered the joint between the three wires, it was pretty much guaranteed you were not going to get an electrical short. But with this, if two exposed leads are connected to the carbon fiber, they will short out. And indeed, that's what happened. I'll show you. Hold on. Hear this? That's conductivity across the whole fin. The whole fin can conduct electricity through it. This is actually true of the body tube, by the way, so we'll have to be careful running cables up that raceway as well, but, we'll burn that bridge when we get there. To fix this, all I had to do was pry each exposed lead up and then pot it using CA. Thankfully, I had only used a pretty light amount to hold the cables down, so it wasn't too hard to do. I used a CA accelerant to speed up the process, and when I was done, I tested all four fins, and all four passed.
Oh my gosh, we're so back, dude. Cool. Wow. Dude, this is such a near miss. This is crazy.
With the extensions in and the servos tested, it's time to pot them all in epoxy. For this, I'm using Loctite E120HP. It's a less viscous epoxy than the 9340, which means it will flow really well into these crevices. Inspired by the epoxy queen herself, Xylofoxlin, I used a little bit of red dye in there too. There might still be some bubbles in here, so since the fins are small enough, I put them inside the propellant bowl and pulled vacuum. Doing this gave me pretty high confidence that we had filled this entire channel with epoxy, crevices and all. After leaving the epoxy for an hour to begin the hardening process, once it was thick enough, I used a knife blade to make sure the epoxy was flat against the surface. You have to go pretty slow on this process to make sure the epoxy has a chance to backfill behind the blade. So a lot of these shots are kind of time-lapse, but the result is really nice. Now that the servos, control tabs, extensions, and epoxy is all in on these fins, the fins themselves should be about done, and we need to attach them to the vehicle next. Even though we have a control system, it's still important that these fins go on straight, so I printed the world's largest fin jig. I did this using the Prusa XL, kindly provided by Prusa with lots of Prusament, and I went fairly slow with it, so it took about 2 days to complete the print. Using Onshape, I can show you a little bit more about how this works. The fin jig almost identically conforms to the exact shape of the fins, and we can be pretty sure about this because we cut the fins on a CNC machine. Because of this chamfer here, as I push the fin down, it should be pushed against the airframe, and that'll be our primary mechanism for making sure that the bond line is pretty tight. The fin jig also has lots of screw holes for attaching it and holding it to the airframe itself, and it has small reliefs near the base so that any excess epoxy that squeezes out doesn't attach the fin jig to the rocket itself. I'm just going to put some superfluous shots of these fins in here. The carbon fiber with the red epoxy with the servo and red control tab looks so cool together, and I'm really proud of how these came out. I've had the idea to embed this servo into these thick fins for a long time now, and it's so cool to see it come to life. Not to tempt fate, but I'm also kind of shocked that nothing has gone wrong so far. Every epoxy operation is basically an opportunity to get something catastrophically wrong, and so far, so good. The airframe for the meat rocket is a 60-inch carbon fiber tube. The tube is wound and then centerless ground down to a precise outer diameter, and the thickness of the wall is pretty thin at about 1.5 millimeters, which we're going to talk about later. I use solvents like acetone and IPA to make sure that the outer surface is clean. We're going to do sanding on the areas where the fins attach to ensure even higher strength, but generally speaking, the whole tube should be clean too. After a test fit in the fin jig, I identified which fins I was most proud of and which fins I was least proud of. The best looking fins get an F for front, the worst looking fins get a B for back. When this thing is on the launch pad, I want those good looking fins to be out front. Safety is a recurring theme here. Anytime I'm working with carbon fiber, anything that can create dust, I'm wearing a respirator and eye protection. And when it's an option, I also turn on an air handler in the garage to slowly decontaminate the space. Here, I'm using 60 grit sandpaper to prep the root cord with some thick gloves to prevent any oils on my hands from getting on the surface. And I'm doing the same on the tube as well. The fins are going to be bonded to the body using Loctite E120HP epoxy, and even though it's going through this mixer tube, I always mix a little extra just to make sure it's homogeneous. With a few drops of black dye and a little bit of time in the vacuum chamber to get rid of those bubbles, we are ready to attach these fins. I first coated the surfaces where I wanted the fins to go and then attached the fin jig by lightly screwing down on each side. You certainly don't want to go too much on this because you can damage the airframe itself. The fins get the same treatment with coating on the E120HP on the root cord, and it's good to do it this way to ensure that the epoxy really gets into all those little cracks. Once the fins were placed in the jig, I was able to loosen it and move it around just a bit. My goal here is to keep the tips of the fin slightly forward of the aft of the tube. The thought is that whenever I stand the rocket up, if I'm working on it, I want it to be resting on the base of the tube and not on the fins. This protects the trailing edges, and the increased bond area should help us keep the fins attached if we have a hard landing. As the fins were curing to the airframe, I started a print on the Prusa XL for some filleting tools. Once the fins had cured, I was able to pull the jig off, and the final product was excellent. The rocket is eventually going to be painted white, but the red with the black carbon fiber is such a cool look. The next step in this process is filleting the fins. The root bond is pretty strong, but it's not strong enough to survive Mach 3. Creating fillets at the base of each joint helps provide extra stiffness and extra strength in flight. And the first step to any epoxy operation is, of course, bond prep, which I'm doing using 60 grit sandpaper, and the epoxy is going to be Loctite E120HP with some black dye. E120HP, as previously discussed, is a very thin epoxy, so it makes it kind of difficult to use for fillets. The ultimate structural properties of the epoxy are phenomenal, which is why I've selected it for this task, but it does require some technique to get it right. And in order to get this technique right without messing up the actual flight vehicle, I did lots of testing beforehand. Several months ago, I began this testing with small 3D printed molds. The goal of each mold was to assess how fast the epoxy would exotherm and when the ideal point to pull the epoxy was. When you pour the epoxy, it is quite thin, but eventually it thickens up, and somewhere in between that time is a Goldilocks zone where pulling the fillet will make sure it maintains its shape instead of slumping back into a chamfer more than a fillet. Getting this right can be pretty tricky, so I also experimented with some other approaches. At a larger scale than these 3D prints, I used one of the old fin cans from Luminaire to test fillet making. On this first test, I used about 1% Kevlar pulp mixed into the epoxy. This did thicken it up considerably, and after about 30 or 40 minutes, I was able to pull a pretty good fillet with a consistent shape. but the surface finish left a little bit to be desired. I'd love to get a smooth surface without sanding, so I reduced the amount of Kevlar pulp to about 0.5%. The surface on this was still a little more bumpy than I would like, so I ditched the Kevlar altogether and focused on getting the timing right. Using pure Loctite E120 HP with a little bit of different colored dye each time, and with the addition of a thermal camera to monitor the runaway of the epoxy itself, I found that it took roughly an hour from the start of the mixing to get the consistency that I wanted for the fillet to maintain its shape. So with this testing done, let's return to the meat rocket. While the epoxy was curing, I had an interesting idea. All of the fraying that had occurred during the milling process meant that even though sanding took care of some of it, there were still lots of little carbon fibers poking up everywhere. I'm handling this rocket quite a bit, sometimes without gloves, and contrary to popular belief, carbon fiber does not belong in your skin. So I took the excess E120 HP and just started spreading it around on the fin. My goal was to create a thin sealant layer on top of the carbon fiber, and I did achieve this, although it really should have been done with laminating epoxy. Like, the final result got me where I wanted to go, but it created a lot of pock marks on the side of the fin, which will ultimately hurt our max speed and apogee. After waiting about an hour, I pulled the fillets. I designed these little fillet tools and printed them out on the Prusa. They should create about a 1.5-inch radius on the fillet, and they also conform a bit to the airframe itself, which should help clean up the excess epoxy. One thing I found is that the servo cables really wanted to float to the surface of the fillet. This is kind of a problem considering that the cables at Mach 3 are not going to be super happy. Once the epoxy had thickened more, I was able to push the cable inward so it was less of a problem, and on the other fins, I CA'd the cables to the surface first before filleting. The E120 HP is thin enough that I had to separate the rocket into quadrants and only do one set of fillets at a time. Each time I poured the epoxy onto the fin, I tried as much as possible to reduce fold over. This is a problem both with epoxy and with the propellant that I make. When a liquid folds over on itself, it doesn't always do so flat like this. It can often entrap air bubbles, and any air bubbles are bad for the propellant structurally and for burning, and they're also bad for epoxy for the same reasons. Well, I guess not for burning, but... So anyway, when pouring this epoxy on, I'm trying to reduce fold over as much as possible. Some of these fins did require multiple fillet pulls. If I didn't quite get it right, thankfully the epoxy is pretty easy to work with, so you can always just add a little bit of extra and pull it again if you don't get it right. And with each set of fins, I also coated the entire surface just like I did for that first set. We're just looking for a really thin layer to seal those carbon fibers in there. It's mostly for handling of the rocket and not for any aerodynamic reason. All sanding is done with 60 grit sandpaper here, and if you want to learn more about sanding and surface preparation, oh boy, I have some great news for you. I spent like a month and a half this summer doing a ton of composite bond testing, and a little bit of a plug, there's a ton of info about it on the Patreon, but the video about it on the main channel will come out in probably a few months. It is an enormous video, so it's going to take a little while to actually make. But anyway, one of the learnings here was like 60 grit sandpaper is pretty good, and acetone and IPA are also pretty good. There's a lot more nuance to it, but that's a future video. One great thing about the E120 HP is that they sell it in these cartridges. I'm using quite a lot of epoxy across this entire project, and the cartridge with a little mixing tube makes that much, much easier. For any given epoxy operation, I just put one of these expendable tubes on there. It mixes it for the most part, and I don't have to measure out my own ingredients. And even though I'm mixing further after it goes through the mix nozzle, I did find that the mix nozzle itself in my composite bond testing was like 90% of the effectiveness. So in that little distance that it travels, it mixes pretty well. Once all of the fillets on the fins were done and cured, I did the same thing that I've been doing every step of the way here, which is that I tested each one of the servos to make sure the fins still worked. And with that test passed, it's time to talk about structural integrity. Whether you're a human or a rocket, having integrity is important. If you're a human, maybe that means sticking to your word when you say you'll do something. And if you're a rocket, maybe that means you don't fall apart at Mach 3 like you're designed not to. Here's the problem at hand. Between the end of the rocket motor case and the beginning of the upper section of the rocket, there's a lot of unsupported area. That unsupported area is that 1.5 millimeter thick wall. Granted, this is carbon fiber, but we're also going to 3 times the speed of sound, and the dynamic pressure on that blunt tip nose cone is going to be considerable, like capital C considerable. So like the vibometer on is 1.5 millimeters too thin is just, the vibes are like not great. So here's what I did to fix that. I took a section of coupler tubing and bond prepped the whole surface. Then I did the same for the inside of the upper section of the airframe. After coating both surfaces in E120HP, I added a little bit of coupler tubing to stay forever forward of the motor section. This leaves a little bit of room for the coupler for the upper section to fit in, but it improves the structural integrity above the forward closure for the motor. Unfortunately, this still leaves a little bit of a gap between the supported motor section and the supported upper coupler section. That gap is so tiny, it probably doesn't matter, but I'm so terrified that this thing is going to fall apart. I've never sent anything to Mach 3, well, okay. I've never sent anything to Mach 3 and had it survive. Let me put it that way. For that reason, I rolled out a sheet of carbon fiber weave and decided to do a small layup on the outside of the rocket to bridge that gap between the forward closure of the motor and the coupler stiffened section. I used 2 layers of carbon fiber, one at 90 degrees, one at 45, and cut out a top layer of 2-ounce fiberglass to smooth out the surface so that I don't have to sand as much. The epoxy I'm using is Fiberglass System 2000 with the 2060 hardener. This is the same epoxy I used for a lot of the Lumineer stuff, which means it's been thermal cycling in my garage for about 3 years now, and it smells like it. If you need a reminder, it used to be this color, and now it's this color. I don't know how much the strength of the epoxy has changed, but it seems to work fine. To make it super clear, if I were making a crude vehicle, I would not use expired epoxy. Okay, moving on. After degassing, I infused it into the carbon fiber weave using a little squeegee thing. In composites manufacturing, it's critical to get the right ratio of epoxy to the weave. That means that for most of these layers, after infusing lots of epoxy into it, I squeegee it out so that there's just the minimum amount involved in the weave itself. Even though there's 3 layers of composite here, it did end up pretty thin, and the transition between each of the 3 layers is pretty smooth. So actually, once this thing is painted, you shouldn't be able to notice the transition that much. The next step we're going to take is running the raceways up the side of the vehicle. This involves taking these PWM cables, running them up the side, and protecting them against the Mach 3 airstream. Much like the servos, this leaves no opportunity for serviceability because at this scale, it's more valuable that I just pot them in epoxy, make sure they work first, but keep them safe in epoxy forever. The epoxy here is Loctite E120HP with a bunch of thermocells added, I think somewhere around 20%. This thickens the epoxy to a point where it should be able to form a pretty good raceway, and I was able to print out raceway forming tools on the Prusa machines. These tools are designed such that they should be able to just about cover the PWM cable and leave a little bit of epoxy on the surface. It took a few tries on a practice tube to get this technique to work before I was comfortable doing it for the full vehicle. And eventually, much like the fillets, I found that waiting about 40 minutes to an hour before actually doing the pull on the epoxy was pretty important to helping the epoxy maintain its shape. And with the test sections done, it's time to attach another PWM extension. Just like before, I'm staggering the connection here to make sure the electrical leads can't make contact with each other. And to minimize the amount of work I have to do on this, I'm running 2 leads per raceway. In an ideal world, we could do all the leads down one raceway. That would be the least draggy solution. However, as the vehicle gains some angle of attack, that one raceway becomes a really big roll control surface, and it can spin the vehicle. So what we want is symmetry. Learning from my mistakes in the past, I used electrical tape to prevent the exposed leads from touching and then shorting against the carbon fiber airframe. I then tacked down the leads using CA and a little bit of accelerant, and as always, I was constantly checking whether the servos were still working through the whole process. Before running the raceway, we also have to pop the cables inside the vehicle. We can't do this lower down on the airframe because it's occupied by that motor. This is a minimum diameter rocket, which means the only way for this rocket to be a smaller diameter is for the case to act as the airframe itself. Basically, that means we have no room to pop the leads onto the inside. And frankly, we wouldn't want to either because it's probably going to get pretty hot around the motor case. Anyway, the leads pop through the very thick section forward of the motor, which is great because it means we aren't losing a ton of structural integrity by drilling massive holes through it. In a lot of this testing, I'm leaving the motor case on the inside of the rocket just to make sure I understand where everything is going to sit, and you can see the forward section of it in this shot. And just for total clarity here, there's no motor in this. There's no rocket propellant on the inside. You don't do that until right before the launch. Just like before, the leads get tacked down with a little bit of CA, and I use some accelerant to speed up the process, and then it's time to finally run the raceways. Getting the leads to be fairly straight was a little bit of a tricky process, especially at the joint between the 2 extension sections. It's just hard to get that slack to all line up when each of the 3 lines becomes taut. Just like in the earlier testing, I'm using Loctite E120HP with about 20% thermocells to thicken it up, and initially I was going to make these these raceways with yellow epoxy, so I added a ton of dye in there, and then it did this really weird thing after vacuuming. It seemed like the dye was starting to separate out from the epoxy, and I got really wigged out by this. The raceways aren't like structural, they aren't critical to the structure of the rocket itself, but I don't want to be putting epoxy on the rocket that's filled with like some type of oil or thing that's going to separate out. So even though this epoxy is kind of expensive, I took the hard decision of ditching the yellow epoxy. One thing you can do is that if you have an epoxy mat like this and it gets really dusty or it's got like paint chips or whatever, you can just slather the epoxy on it and then wait for it to cure and pull it off, and it makes this really cool hexagon shape. I am not sponsored by Total Boat, but I got the mat from Zyla and she gave me that little tip. I don't mean to toot my own horn super hard, but pouring this raceway was like one of the most satisfying things I've ever done. It was a little harder to get a smooth surface toward the fin, and I think this is just going to take some sanding later on. And just like on the tests, I waited about an hour before I pulled the actual raceway shape using a much larger tool that I designed. The final result was like not amazing. There was a lot of excess epoxy that ended up on the side of the booster, and I realized a little too late that it was pretty easy to lose track of where the PWM cable was within the raceway, which meant that it was easy to run the raceway a little offset from the cables themselves, leaving them fairly unprotected. So it took a couple of tries to get this right, and in the future, it seems like it'd be way easier to just fiberglass like layup over the cables themselves. On the second raceway, I used a little bit of black dye in the epoxy, and although it was satisfying and looked cooler, it was harder to index against the PWM cables, i.e. the problem of earlier, which is forgetting where the PWM cables are located within the raceway itself, gets harder when you add black dye. I did my best to clean up the excess epoxy around the raceway, but there wasn't a ton that I could do to like remove it. At this point, I've made peace with the idea that there's going to be a lot of sanding in my future, and there's very little I can do to avoid that. Moving on, there's this thing that happens when a project takes long enough where you begin to overthink anything that you are able to overthink. The way that this manifested for me is that I started to become concerned about the unstiffened section at the upper part of this tube. We had already stiffened the section forward of the forward closure, and the very top of the tube should be stiffened by the coupler that will sit within it. But I was starting to get concerned about the integrity of the tube itself up there, and it felt like very little effort to add just another layup, so that's what I did. I bond prepped the crap out of the surface, and then I cut out some more carbon fiber weave.
Toby.
I also cut out some 2-ounce fiberglass so that we wouldn't have to sand the final surface and it could be pretty smooth on its own. And then I infused that expired epoxy into the carbon fiber weave. One benefit of doing this layup after the raceway is that the carbon fiber ended up covering the sort of leading edge of where the raceway pops into the airframe. So there's a little bit of added protection on that servo cable sort of inflection point. Once all the layers had been laid up, I waited a few hours for the epoxy to become tacky, and then I cut the edge off with a knife. The actual thickness change here, and especially aerodynamically, is almost nothing. And in my opinion, the added structural integrity like makes me sleep a lot easier at night, knowing that like that's probably not how this is going to fail. If it fails, it'll probably be something else.
We will not have a structural failure. One more time. We will not have a structural failure. The haters said I couldn't do it. I'm going to try to make sure they're not right. But if they are, it won't be structures.
As I mentioned earlier, I knew I would have a lot of sanding in my future, and as it so happens, the future has arrived. I'm doing all of this sanding outside because of how much dust it creates, but of course I'm also wearing a respirator, safety goggles, and gloves. An orbital sander with 120 grit sandpaper ended up working pretty well for most of this stuff. My primary focus was on smoothing out any bumpy transitions, specifically the transition into and out of the raceway, transitions between the layups, and all of that bumpy epoxy that ended up on the surface of the fins. I said it before, and I'll say it again, I wish I had done this with laminating epoxy. It was the wrong tool for the wrong job to use structural epoxy for this, but what are you gonna do? I guess you're gonna learn from it. With the sanding done, the booster looks no different, but it'll become apparent once we put a coat of paint on that it's much smoother than before. Before that coat of paint though, we need to add some rail guides. The meat rocket's gonna launch from a 15-15 rail, which is more accurately described as a 1.5 inch by 1.5 inch T-slot extrusion. I printed the rail guides out on the Prusa XL, which is comically large for the task at hand, and they're made out of PLA Prusament. You might remember that this rocket is going to Mach 3, and if you're wondering, hey, won't those melt off at Mach 3? You're probably right. They probably will, but from a drag perspective, it's almost better if they melt away, and I don't intend on flying this vehicle a bunch of times, so PLA should work just fine. This could be a video on its own, but I think engineers hyper-optimize for problems that don't actually exist, and this is one of those things. PLA needs to be strong when it's on the launch pad, and especially because I'm going to be launching in the winter months at FAR, we're not going to see these prints melt on the launch pad. These are getting painted white so they won't thermally absorb a ton of energy, and they melt off in flight, which is kind of good. Anyway, moving on. As before, as testing goes on, I keep testing the servos to make sure everything is totally functional, and after sanding, everything looked good, which is a little bit surprising because I had a couple of close calls. In this shot, you can see one of the white traces from the PWM cable sticking out because I have sanded into it. The wires inside this cable, like the non-insulation material, is still fine, but the insulation has been eroded away by the orbital sander, so your boy came real close to a problem here. This actually happened in several spots, and the only cable that seems to have been affected in most of them is the signal cable, which is the only cable that doesn't need to deal with a lot of current, so thank goodness. I mixed up yet another batch of Loctite E120HP epoxy, and I used it to epoxy on the rail guides and do a little repair work on these exposed wires. I also used this opportunity to further coat the leading edges of the fins in that Loctite E120HP. My goal was to seal the surface just a little bit further. I'm getting more and more concerned about the sharp edges on this rocket as it hits Mach 3, and so it can't hurt to have just a little bit of extra epoxy on the tip. To prep this thing for a coat of paint, I brought it back outside to prep for yet more sanding. And as shown in this clip, this is why you want to wear a respirator and safety glasses and gloves and protect yourself as much as possible. All these little particles are sharp, and all of them will rip up your lungs as long as you let them. With sanding, I primarily focused on the leading edges and the area around the rail guides, and once that was done, I wiped the whole vehicle down with a coat of isopropyl alcohol to ensure that it was clean and ready for a coat of paint. I'm using these huge white glossy spray paint cans, and I've had a couple of problems with them before, but one thing that I've found to be really helpful in prepping for spray painting is putting them in a bucket of hot water. Not like boiling hot, but warm enough for 10 or 15 minutes to make sure that you can get the paint inside as flowy as possible. Especially if the spray paint spends a bunch of time in a cold climate or you're in the winter months, it helps to warm it up just a little bit. Before painting, I also taped over the red anodized control tabs. I spent money to get these anodized, so I want to preserve the color. I also prepared a witness sheet, or rather a witness piece of cardboard. This is a part that gets spray painted at the same time as the rocket, and so if I want to add extra coats of paint or change colors, I can test paint compatibility on this sheet before putting it on the rocket. The best tip that I can give you for spray painting is to go in light, short passes. It's very easy to overcoat and end up with drips in your spray paint, and so going slowly and being patient during the process is important. This is not the final product, this is not the final paint scheme, but rather a base coat, but it's going to be a stopping point for today. The white rocket with these red tabs looks excellent, but it's going to look even better with the full paint scheme, which is much more detailed. I'm actually kind of excited to see how much this paint scheme gets damaged from what's referred to as Mach rash in the hobby community, and that's where your rocket goes so fast that the paint actually begins stripping off. But the build looks a lot better with a single coat of white paint than it did with all of those mismatched colors of epoxy. Looking at this in the sunlight, there are lots of things that I wish I had done differently, but that's why I build things, and that's kind of why I put them online too. If you look at this build and you think to yourself, wow, I can't believe he did it that way, great. Go try something different and put it online so that everyone else can learn from you. For instance, this raceway should have just been a layer of fiberglass. These fins should have been sealed with laminating epoxy. And I wish I had done a little more sanding at the aft to make these surfaces less rough. But overall, I'm really excited to get this thing in the air. And before we do that, we have to make a bunch more parts. I've got a nose cone to make, I've got a copper tip to apply, I've got avionics to build and simulations to run. There's a lot more to come, as always. You should subscribe if you're into that kind of thing. And if you just can't wait, I publish a video about every 2 weeks on Patreon that's updating you on what I'm doing right now. Some of these long videos take much longer to put together, and so if you want to know what's going on every 2 weeks, I publish videos there, and it's like $5 a month, and it supports the project. Anyway, I appreciate you watching this long. This is a long video, but I just wanted to put all this stuff on the internet, and hey, it's no effort November. So thanks so much for your time. Thanks for watching. Thanks for hanging out. I hope you're having a great November, and that's all from me. My name is Joe Barnard. May your skies be blue and your winds be low. Goodbye.